All right, so let's check out practice 11.14 here, the first problem. And I've gotten all written out. And the first thing they want is the derivative function. So we're going to need f of x plus h. So we'll just plug x plus h into the original function. And then we'll take this and plug it all into the limit. So f of x plus h is and then we have minus the original function. Oops, I might have wrote a little too big here. And now we have all our information plugged in. Let's distribute everything out. So x plus h squared is x squared plus 2h plus h squared, and then the minus sign will distribute across all that. So we get a minus x squared minus 2hx minus h squared. Distributing the next part. And then distributing the minus sign into the parentheses there. And so there is everything distributed out. And so now we'll gather like terms. So what do we got? We have positive x squared and negative x squared. We'll subtract out. Plus 6 and minus 6 we'll subtract out. We have minus 9x and plus 9x. Those will subtract out. And so we're left with and there's a h factor in the numerator. And there it is. Our h's now divide out. And so we're left then for the derivative. So as h gets forever smaller, this is going to 0. And then what this is forever approaching is minus 2x plus 9. And that is the derivative function. So this function will tell us the slope at every point of the original function. And this is actually the first thing they want filled in here. And so now they just want to know what f prime of 1 is. So we'll just plug that in. Now they want to know f prime of 2. Okay. We'll just plug it in. And then f prime of 3, I guess I'll write that over here. So plugging in 3, what do we get? Plugging 3 into this, so minus 6 plus 9. And there's the first question. So number 2 here. So we have the function 108 divided by x. And we got our definition of the limit of the derivative here. And again, the first thing we're going to need is what is f of x plus h. So we'll just plug that into the function and get 108 over x plus h. And so we'll plug this stuff into the derivative. So f of x plus h is 108 x plus h minus the original function, all divided by h. So here we have two fractions in the numerator. So to deal with these two fractions in the numerator, we'll find a common denominator and bring them together. So the common denominator there would be x times x plus h. So just multiplying this denominator times this one will get us a common denominator. And so that means we have to multiply this by x over x. And we multiply this by x plus h over x plus h. And so we will get then 108x minus, so be careful here, this is minus 108 times x. And then this is minus 108 times h. And this is all over h. So if you notice in the numerator then, this subtracts out. And so we're left with minus 108h over x plus h. Now remember, division by h is the same thing as multiplying by the reciprocal. And then you can see these h's here will divide out. And so we're left with minus 108 over x plus h. And that's the limit we're trying to take here. So as h gets forever closer to 0, then this limit is forever approaching minus 108 over x squared. And that is our derivative. And so they want to know f prime of a minus 6. Okay? So we currently have the derivative function. And now we're just going to plug some numbers into it. So they want f prime of minus 6. And minus 6 squared is positive 36. And we can do some simplifying there. I guess good old division by 2 because we have even numbers. And there's actually a factor of 9 in common here. Actually, this is 3. 54 divided by 18 is 3. And that's our answer. So now we have f prime of 0. So now look right here. So here's the derivative function. They now are asking us to plug in 0. Well, if we plug in 0, we'll get division by 0, which means the derivative does not exist at 0 because you have division by 0. So the derivative, so f prime of 0 does not exist because that causes division by 0 and that causes the derivative to fail. And then f prime of 3, so we'll plug 3 into this. And 3 squared is 9. And can we simplify that at all? We can. 3 would go in here 36 times. 3 goes in there 3 times, and that is actually then 12. And there is question 2. All right, so number 3, got it all written out there. So now we have a square root function, and here's our definition of the derivative. And like always, we are going to need the x plus h part. And so we'll plug that in to the function. And now we'll plug all our information into the derivative. So g of x plus h is 13x plus h square root. And then that's a real lazy h right there. And then we have subtracting off the original function and all divided by h. So to deal with this, to deal with these square roots, normally when you have square roots, you square both sides. That's how you get rid of a square root, by squaring both sides. But we can't do that in this case because we don't want to square. We don't want to square this notation here. We don't want to square that because that's the derivative notation. So to handle this, we use the conjugate. So if you recall, the difference in squares, a squared minus b squared, is a plus b, a minus b. The only difference is the plus or minus there. They're both a and b. So in other words, if we have a plus b, and we just choose to multiply by something that changes the sign, then we know this is the difference in squares, and it'll always be a squared minus b squared. This squaring right here is how we can also get rid of square roots. So what we're going to do is we're going to think of this as a minus b. And so we'll multiply this then by a plus b. And I'm not going to have enough room here. Let me rewrite this out. So we're going to multiply this by a plus b over a plus b, where this is a and this is b. So let me write that out again here with some more room. So we're going to multiply the top and bottom by the conjugate. So instead of a minus sign, we're going to have a plus sign. So there we go. This whole thing in the parentheses is the conjugate. It's the a plus b part. So again, all I did was change the sign here, this minus to a plus, because now the numerator is a difference in squares. So when we distribute this, so this times this, doing FOIL, square root times a square root will get rid of the square root. Now this first term times the second term, and this second term times this first term will always subtract out with difference in squares. And so the last thing to do is minus square root of 13x times positive square root of 13x, which would give us then a minus 13x. And then in the denominator, we want h to divide out. So we're not going to distribute h because we want h to divide out. So we want to keep it as a factor. And so this is where we're at. So again, the maneuver here is right here, the conjugate. And now if we look where we're at, we're the limit here. So this is 13x plus 13h minus 13x. So the 13x's will subtract out. And we're left with then 13h over h, and then times this stuff. And notice the h's now divide out. And so our final limit is 13 over this stuff. Now as h goes to 0, so here's the only h right here. As h goes to 0, what's left over? Well, what's left over is a 13 in the numerator. And then from this part here, the h is going away, so we just have square root of 13x, and then plus the square root of 13x. Since the denominator, since these are like terms, means we can add them together to get our final answer then of this for our derivative. And then it's going to want us to plug in some function values here. I've completely run out of room on that piece of paper. Try another one here. So let me try to keep this function in. So here's our derivative. And now they want to know, well, what is g prime of minus 3? Well, let's plug that into the derivative. Now notice, this will cause us to take the square root of a negative number. And you can't take the square root of a negative number, so this derivative doesn't exist. And now they want us to check out g prime of 0. So plugging 0 into our derivative, so again, we have another problem, division by 0. That's a failure. This derivative does not exist. And then finally, we have g prime of positive 3. So let's plug that into our derivative. And then 13 times 3 will get us a 39. And this is a real, that exists. So there's our first answer that exists for this problem. And that is question 3. All right, so here's number 4. Got the stuff written down. Notice there's an x cubed here, which means this is going to have a lot more algebra in this one because of the x cubed there. And like always, we're going to need that starting spot of f of x plus h. So we'll just plug that into the function. And there is our information to plug all into the definition. And I'm going to leave myself plenty of room here. So we're going to plug this into the derivative. And then we subtract off the original function. Now the original function does have multiple terms. So we'll have to use the parentheses here to make sure the minus sign distributes correctly. And here is then the limit. And we need to distribute all of this stuff out. So because x plus h cubed is a lot of distribution there, let's just focus on this first. So this is x plus h times x plus h squared. And x plus h squared is x squared plus 2hx plus h squared. And now we'll have to distribute all this out. So I'll distribute the x to everything. And now distribute the h to everything. And barely got it all in there. So there is x plus h cubed. And now looking back at the derivative, you can see we're going to multiply all of that by 4. And so that's what I'm going to do now. I'm going to take this 4, multiply it all by this x plus h cubed as the next step in writing out the derivative here. So it's going to be, so again, I'm doing this part right here. So I'm going to do 4 times all this stuff. There we go. And all of that is just this part right here. So now we have the plus 10. And now we have the minus sign that distributes into the parentheses here. So we get a minus 4x cubed and a minus 10. And all of this is over h. So there it is. I can't even quite fit that all on the screen. There it is. Let's gather like terms. So plus 10 minus 10. Gone. Minus 4x cubed and plus 4x cubed. Gone. And that's it for subtraction signs. So let's gather like terms. So we have an 8. So we have an hx squared. We have another hx squared somewhere. Here's another hx squared. So 4 plus 8 will give us a 12. So I'll take care of this term and this term. Now here we have an h squared x. Here's another h squared x. So we have 4 and 8 to get us a 12. H squared x. And that gets rid of those terms. And so now all that's left is the plus 4h cubed all over h. So that cleaned up pretty well. And the numerator has a h that we can factor out. And now that h in the denominator will divide out. And so the limit we're going to take then, after all is said and done with all the simplifying here, 12x squared plus 12hx plus 4h squared. So if we look at this now, as h gets forever closer to 0, so this whole thing right here has an h in it. So this whole term is going to 0. This also has an h in it, which means this whole term is also going to 0. And all that's left will be 12x squared. And that is our derivative. And it wants us to find some values here. Let me get another piece of paper since I used that one up. So our derivative, actually the derivative is so small, let me just write that again. Well, small, easy to write, I mean there. So there's our derivative. And now we're going to plug in minus 3. So minus 3 squared is 9 to get us a 108. And now we want f prime of 0. All right, well, 0 times 12 is 0. And then we want f prime of 2. So that's 12, and 2 squared is 4. Get us then a 48. And there is question 4. So looking at number 5 here, I know it says a bunch of stuff here about the secant line and a tangent line. And their first question is, what is the equation of the secant line? And remember, the secant line is a linear function. But for the secant line, m is your standard slope formula. So let's look at what we have here. If we go back to the MyMathLab screen, it's telling us x equals 2 and x equals 5. So x2 is larger than x1, so x2 is the larger number, which is 5, and x1 is the smaller number, which is 2. And now to get what y2 and y1 equal, we have to plug these into the function. So let's look. If we plug 2 into the function, we'll get 2 squared plus 2, which is 6. So when we plug in 2, y1 is 6. How about x2, 5? If we plug in 5, we'll have 25 plus 5, which is 30. And so here's our x1, x2, y1, y2 that we can then plug into the slope formula. Eight. So the slope of our secant is 8. So this is what we have so far. We just figured out the slope is 8. The slope of the secant line. This is the actual secant line we're trying to figure out. And again, the slope of the secant line is just your traditional old slope function, slope formula. Now, to finally determine the y-intercept, we just need one of these ordered pairs. It doesn't matter which one. I'll just choose the one with the smaller number. So if you plug in 2, you get 6. So this one right here, plug in 2, you get 6. So this is saying when y is 6, x is 2. And so we'll have 16 here. Whoops, that's an equals there. And so b equals minus 10. And so our equation for the secant line is 8x minus 10. All right, sorry, I had an interruption there. So the secant line, 8x minus 10. Let's check that answer. There we go. And now they want the tangent line. So that goes back then to where I started originally with writing this down. To get the tangent line, now again, the tangent line is again a linear function. However, for the tangent line, the slope is the derivative for the tangent line. So we need the derivative. So the first thing we're going to need is f of x plus h. And again, here's the function right here. So we're just going to plug x plus h into that. And now I'll take all our information and plug it into the definition of the derivative. And now we're minusing the original function. Since the original function has 2 terms, we got to use a parentheses here to make sure the minus sign distributes correctly. And that's all divided by h. So we'll distribute everything in the numerator and try to clean that up. Let's see what we got. So we have a minus x squared and a positive x squared. Gone. And we have a plus x and a minus x. Gone. And what's left over and we have the h that we can factor out in the numerator. And now those h's divide out. And so the limit reduces, simplifies all the way down to 2x plus h plus 1. So now as h gets forever closer to 0, this limit is getting forever closer to 2x plus 1. And that is the derivative. Now, the derivative gives us the slope of the tangent. Now, we do need to choose at which point we take it at, because they did give us 2 points. They gave us x2 and x5. So we can only, well, we can do it both of them, but my math lab's only asking for one of these. So let's check out what it says for part B. It says the equation of the tangent line when x has the first value. So x equals 2 then. So in other words, we want to know what is the derivative when x equals 2. And that's 5. So the slope of our tangent line is 5. The last thing to do is to figure out the y-intercept. And to do that, we need an ordered pair. And if you recall, we use the ordered pair 2, 6 for the secant line. We can also use the same ordered pair again for the tangent line. Remember, the ordered pair is a point on the function, and this has to cross that point. So when y is 6, x is 2. And that's getting really crunched in there. So we have 5 times, that's a horrible 2. 5 times 2 is 10. So we'll have 6 minus 10 is what b is. So b is minus 4. So our final answer here is going to be the slope 5 that we found. And we just found b is minus 4. And that's the equation of our tangent. And I want to show this in Desmos really quick. Okay, so I just pulled up Desmos and plugged this stuff in. So if you look to the left here, the first equation I have graphed is the original function. The second equation, which I don't have graphed yet, but there's the secant line. And the third equation is the tangent line. So let's just take a look at this graphically. So x squared plus x, that's the red function you're seeing. Now, the equation of the tangent line means we're picking point 2. So point 2 is right here on the function, and point 5, which is going to be about right here on the function. We're going to take these 2 points and connect them together with a straight line. If we did the secant right, then that's what we should see. So here comes the secant. There it is. So you can see the secant at 2, 6. So here's the point we use, 2, 6, to find the y-intercept. And you can see the point 2, 6 is on the red function. And then this blue line, the secant line, connects the next point, which is 5. And so the blue line, you can see, is the secant line. It connects these 2 points on the function with a straight line. Now the tangent line we did for 2 at x equals 2. Now the tangent line is going to give us the slope right at 2. So if we did the tangent line correctly, we should have a linear function that just touches the function at 2 and gives us that slope right at 2. The green line here is the tangent line, and the tangent line is exactly the slope you have right at 2. And so putting it all together, this is what it looks like. So the blue line is our secant, the average rate of change, and the green line is our instantaneous rate of change, the tangent line. So let's do another one of those. All right, so number 6 here, they want us to find the equation of the tangent line again. So the secant line. The secant line is a linear function, and the slope of the secant is your standard slope formula. So let's look at the information given. For the secant line, we have the points 4 and 9. So x2 is 9 and x1 is 4. We will now take 4 and 9 and plug them into the function, which is 9 over x. So if we do that, if we plug x1 in, we get y1. So y1 is 9/4. And if we plug in x2, we'll get y2, which is 1. So we get 9 divided by 9 for x2. We'll plug this information into our slope formula to figure out what the slope is then between these 2 points. So in the numerator here, 1 is 4 over 4. So 4 minus 9 is a minus 5/4 in the numerator. And 9 minus 4 is 5 in the denominator. And remember, division is exactly the same as multiplying by reciprocal, which means those 5s divide out, and you're left with minus 1/4. That is the slope of the secant line. And now to figure out the y-intercept, we need to choose an ordered pair up here. I'm going to choose the ordered pair that's easiest, the one without the fraction. So that ordered pair then is 9, 1. And that's what I'm going to plug in. So when y is 1, x is 9. One again is 4 over 4. So we get for the y-intercept 13/4. So our final answer for the secant line is that. So now we want the tangent line. So the tangent line is the one that requires the derivative. So again, the tangent line is a linear function, but for the tangent line, the slope is given by the derivative. So we need the derivative. So our function they're giving us is 9 over x, which means that f of x plus h is 9 over x plus h. And we will plug all this stuff into the definition of the derivative. So f of x plus h is 9 over x plus h. Then we subtract off the original function. The original function is 9 over x. And all of this is divided by h. So this is something we did previously. When you have fractions, you should get a common denominator and combine these together. So the common denominator here is going to be x times x plus h. So that means we're going to multiply this by x over x, and we're going to multiply this by x plus h over x plus h to get those common denominators. And that will give us then a 9x from this one. And then remember there's a minus here, so it says minus 9x. And then minus 9h. So technically there should be parentheses around here. Got a little lazy there. And 9x minus 9x subtracts out. Gone. So we're left with, oh, I'm sorry, I forgot. All this is divided by h still. Forgot about that part. So rewriting this again, so we have in the numerator minus 9h, x plus h. Now, everything divided by 0 is exactly equivalent to multiplying by the reciprocal. So these h's will divide out. And we're left with minus 9 over x times x plus h. Now, as h goes to 0, then this limit is forever approaching minus 9 over x squared. And that is our derivative. Now, ultimately, we want the tangent line. Remember, the derivative will give us the slope, but we need to know the point where. So let's look for part B, the tangent line. We want the tangent line to be at x equals 4. So we'll figure out the slope for the tangent line, which is the derivative, and they want us to find it out at 4, so that's what we'll plug in. And so we'd have minus 9 over 4 squared. And that's our slope. So for the tangent line, we just figured out the slope. Now to figure out B, we'll use the ordered pair. And the ordered pair I used the last time was 9, 1. And I can't do that anymore because 9 is not part of the tangent. We have to use 4. So if we plug in 4 as x into the original function, so if we plug 4 into the original function, we get an output of 9/4. So this is the ordered pair we're going to have to use because our point of interest is 4. So we have to use 4. Let me take this and just kind of go over here a second. So actually, let me just write this all down again. And we have the ordered pair 4, 9/4. And we're going to figure out what B is. So when y is 9/4, x is 4. Now 4 and 16, so that 4 will cancel out to get us a 9/4 there. And of course, bringing this to the left side will mean we add it together. And so we would get 18/4, which can be reduced to 9/2. And that is B. So now we have our final answer for the equation of the tangent line. And there it is. Okay. And now it works. Well, there you go. There is question 6. Question 7, another secant tangent. So again, for the secant line, it is a linear function. And for the secant line, you have your standard slope formula. And if we look back to the MyMathLab question, they're telling us that x2 is 4, and x1 is 1. That's what they're telling us here. Now I'm going to plug 1 and 4 into the function to find out what these y values are. So if we plug 1 into the function, we get 7. And if we plug 4 into the function, well, square root of 4 is 2. 2 times 7 is 14. So now we have the pieces to figure out the slope. Seven-thirds. So we now have the slope of the secant line. And now we'll use one of these ordered pairs. I always like to choose the one with the smaller numbers. So the ordered pair 1, 7 is we'll use here to figure out b, the y-intercept. So when y is 7, x is 1. So we need to get a common denominator here. And there's our answer for B. So the equation of the secant line, and there it is. So let's check out the tangent line. So again, the tangent line is a linear function. However, for the tangent line, the slope is given by the derivative. So we need the derivative. So we know what f of x is because they're telling us it's 7 square root of x. We then need f of x plus h, so we'll just plug that into the function, and so we'll get square root of x plus h. Now that we have this information, we can plug it into the definition of the derivative, and we will get so f of x plus h is 7 square root x plus h. And then we subtract off the original function. So we subtract off 7 square root of x, and all that's divided by h. So here's where we have another example of square roots in the numerator. And to deal with this, we use the conjugate. So the conjugate here is exactly the same thing, except we switch the sign between the terms. So instead of a minus sign between the terms, we now have a plus sign between the terms. Again, this is called the conjugate. And we're going to distribute all that out. Now, what's nice about the conjugate is when we distribute this out, the FOIL method, only the end terms will survive. Because there's a plus and minus here, means the middle terms will always subtract out. So if we multiply these two together, 7 times 7 is 49, and square root times the square root gives us just what's underneath the square root there. Now what I'm saying is this times this is exactly the same as this times this. The only difference is one's plus and one is minus, so they always subtract out. So the last thing that's left are the two others we'd multiply together then. So minus 7 times positive is 7, and square root of x times square root of x is x. And then this is all over the denominator, h, and this stuff here, don't distribute that out because we want the h to remain a factor. because while it remains a factor means we can then divide it out. So here's where our limit is at right now. If you look right here, we have 49x plus 49h. So 49x will subtract out with this minus 49x. And so what's left in the numerator is 49h. And then that's all divided by h. And now notice, this is why we want to keep h as a factor, because now these h's will divide out. And now the limit is doable. So now as h gets forever closer to 0, what remains? Well, what remains is the 49 in the numerator. This h is going to 0, so all that remains there is 7 square root of x plus 7 square root of x. The denominator has like terms, so we can add these two together. 7 plus 7 is 14. And this is our derivative. Now, the derivative is just one part here, though, because they ultimately want the tangent line. Remember, the derivative gives us the slope of the tangent line. So here's our derivative. And looking at part B, we need a point of interest. So let's see what it says for part B. It says when x has the first value, so that means x equals 1. So we want to know, what is the slope of this function at 1? And that's what the derivative is for. So we'll plug in 1. And there's our slope. The slope of the tangent. So we have and then to finally figure out the y-intercept for the tangent line, we need an ordered pair. And the ordered pair we're going to have to use here, because our point of interest is 1. And so if we plug 1 into the original function, we get 7. So that's the ordered pair we're going to have to use here. So when y is 7, x is 1. Seven times 14. And what do we got there? 49 again. And that is B. And now we have our answer, the equation of the tangent line. And there's question 7. Question 8. I don't think I'll need a piece of paper for this one. Find where the graph does not have a derivative. Now remember, the condition for the derivative existing, the function has to be continuous. So continuous means a solid line. So the graph they're showing us, this graph is everywhere continuous. So that's good. The other condition for the derivative is there can be no sharp corners. And you can see at 3, we have a sharp corner. So the derivative will exist everywhere on this function except at 3 where the sharp corner is. There are no derivatives at sharp corners. Because remember, the derivative is ultimately a two-sided limit. And approaching from the left gives us a slope that's going negative. But approaching from the right gives us a slope that's positive. The left and the right slopes do not equal at 3. And that's something that always happens at sharp corners. So this function does not have a derivative at 3. And that's number 8. And let's check out number 9. And let me just read exactly what the question says here. The function is not differentiable. And, this is what I'm looking for right here. We're interested in the interval of -1 to 7. So -1 to 7. So -1 is right here. To 7 is then over here. Now, something else that's important is notice the inequality. Well, let me write this down. Notice the inequalities here. This does not say equals. So this is called inequality notation. If we put this back into interval notation, it looks like that. And if we put this interval notation, it looks like this. So in other words, no equal signs means the endpoints are not included. Equal signs mean the endpoints are included. And that's important here because if you look at the graph, you can see at -1, there's no derivative at -1 because there's no left side. However, -1 is not included because -1 doesn't have an equal sign. So we don't include -1. So our next point where it's not differentiable is here at 1, the sharp corner. So this sharp corner at 1 is not differentiable. Now we'll move along to the function here. This is all good because it's continuous, it's a solid line, and then we run into a problem at 3 because at 3 there's a hole. A hole is not continuous, which means there's no derivative at 3. There's no derivative at a hole. The function has to be continuous for the derivative to exist. So moving on from 3, we're cruising along the function, and now we run into a problem at 5. Because at 5, there's a gap here. The derivative does not exist at a gap because the function is not continuous. So 5 is another problem. And then finally, if we look at 7, 7 is also a problem because there's no right-sided limit. So the derivative doesn't exist at 7, but 7 is not included as an endpoint because it's got the parentheses. There's no equal sign, which means we don't include 7. And so here's our answer then, 1, 3, and 5. And there it is. That's practice 11.4.